Good morning, class. Settle in, because today, we're cracking the case wide open. Ever wonder why there are some foods that boast healthy fats, while others carry a trans fat warning? Well, today, we're exploring the crucial role of double bonds in fatty acids. It is a game of molecular geometry where a single atomic decision changes everything. Today, we'll be discussing the structure and bonding of fatty acids, the physical properties of fatty acids, its health implications, and lastly, the industrial relevance. By the end of our lesson, you'll be able to define cis and trans isomerism in unsaturated fatty acids, differentiate cis from trans configurations by their molecular shape, relate molecular shape to physical properties, explain the impact of cis versus trans fats on cell membranes and health, and identify common dietary examples of cis and trans fatty acids. But before we get into today's lesson, let's see what clues you've already gathered from your previous assignments. Now, who can tell me anything they've observed about cis and trans isomers? Correct! They are molecules with the same chemical formula and atom connectivity, but they differ in the spatial arrangement of atoms around a double bond. Now let's look at these pictures of food. If you had to choose based purely on their appearance, which would you rather do? Interesting choices. What you're seeing here isn't about taste. The main difference about these foods often comes down to the types of fatty acids they contain, and specifically the isomer present. Today, we'll learn why one is usually liquid at room temperature and the other is solid. Let's start with the basics. Who can remind the class what a fatty acid is, and how are they generally categorized? Fantastic! You're right. Fatty acids are the building blocks of fats, and we primarily categorize them as saturated or unsaturated. It consists of a carboxyl group at one end and a long hydrocarbon chain at the other end. Now, thinking about just the unsaturated fatty acids, what do you think is the key structural feature that makes them unsaturated? Precisely. The presence of double bonds in their carbon chains is what makes a fatty acid unsaturated. Now, this brings us to a very important concept in organic chemistry: isomerism. Has anyone heard of this term before? Well, isomerism is when two or more compounds have the same molecular formula but different arrangements of atoms. Think of it like having the same sets of Lego bricks, but you can build different things with them. See how these two molecules both have 4 carbons and 10 hydrogens? But they're connected differently. Let's look at more examples of isomers. Here we have the isomers of butanol. As you can see, they look similar but are different in one or some molecules. There are different types of isomerism, but for today, we'll focus on how it affects our fatty acids. Understanding isomerism is absolutely critical in chemistry because even tiny differences in how atoms are arranged can lead to drastically different physical and chemical properties of molecules. That's why one substance might be a medicine and the other might be toxic, even if they have the exact same number and type of atoms. For example, thalidomide. Thalidomide exists as 2 different isomers, specifically enantiomers. These 2 enantiomers are like mirror images of each other, much like your left and right hands. One enantiomer of thalidomide was an effective sedative and was used to treat morning sickness in pregnant women. The other enantiomer, however, was a potent teratogen, meaning it caused severe birth defects in babies of whose mothers took the drug during pregnancy. Moving on, can you think of any everyday examples where you might be able to encounter substances that are isomers even if you didn't know the term? Great ideas! And for a quick review, we have structural isomers, which are what we just looked at. Same formula, but different bonding arrangements. Now let's zoom in on that double bond we talked about in unsaturated fatty acids. What happens when a molecule has a double bond between 2 carbon atoms? Exactly. Unlike single bonds that can rotate freely, a double bond locks the carbons in place. This restriction is super important because it leads to a special type of isomerism called geometric isomerism, or more commonly, cis-trans isomerism. Now let's look at the cis configuration first. Notice how the hydrogen atoms on each side of this double bond are on the same side. This is same side arrangement. creates a distinct bend or kink in the hydrocarbon chain. Imagine your knee bending. Now compare that with the trans configuration. Here, the hydrogen atoms are on opposite sides of the double bond. This is called opposite side arrangement, allowing the chain to remain much straighter, or more linear rather. Think of it as a straightened leg. These differences in shape are a big deal because a cis fatty acid with its bend can't pack together as tightly with other molecules. This loose packing means it takes less energy to separate them, leading to a lower melting point and often making them liquid at room temperature. Think of a pile of bent hangers. They don't stack very neatly. On the other hand, trans fatty acids, because of their straighter shape, can pack together much more closely and neatly. This tightly pack requires more energy to break apart, resulting in a higher melting point and making them more likely to be solid at room temperature. Imagine trying to stack those straight hangers. Much easier, right? So looking back at all our initial pictures of liquid oil and solid oil, how can your understanding of cis and trans shapes explain why one is liquid and the other is solid? That's a fantastic job connecting those ideas. You can clearly see how even a small difference in molecular arrangement, like a cis or trans double bond, can have a huge impact on the properties of the fats we consume every day. Now let's take a moment to look at how molecular shape influences physical properties, specifically in cis and trans isomers of unsaturated fatty acids. On the left, we see the two isomer types, cis and trans. The cis isomer has a bent or kink shape. This bend happens because the hydrogen atoms are on the same side of the double bond, causing the molecule to twist. As a result, cis molecules can't pack tightly together. Think of it as trying to stack bent paper clips. They don't fit neatly. This loose packing leads to a lower melting point, which is why cis fats are usually liquid at room temperature, like olive oil. In contrast, trans isomers have a straighter shape because the hydrogens are on opposite sides of the double bond. These molecules can pack much more tightly, like stacking straight pencils. This tight packing raises the melting point, making trans fats solid at room temperature like margarine or shortening. So just from the shape alone, we can predict some key physical behaviors, and this is really important in understanding things like membrane fluidity in cells or why some fats are considered more harmful than others in our diet. But let's take a moment to think. How do you think this packing ability could affect how these fats behave in the body, or how even food companies use them? Let's begin with the basics. Our cell membrane is made up of something called a phospholipid bilayer. This structure acts like a protective barrier, controlling what enters and exits the cell. But did you know that the type of fatty acids within this membrane, whether they are cis or trans fats, can actually affect how flexible or rigid the membrane is? This flexibility is important because it directly impacts how well our cells function. Now let's take a closer look at cis fats. These fats have a bent or kink structure, which prevents the molecules from packing together too tightly. So this loose packing would increase membrane fluidity, making cell membrane more flexible. And remember, flexible membrane is a healthy membrane. Now this helps with cell communication, movement of synthesis, and overall cell performance. In contrast, trans fats have a straight structure, which allows the fatty acid chains to pack closely together. This results in a more rigid and less fluid membrane. A stiff membrane limits how well the cell can transport nutrients and signals. Over time, this can negatively impact cellular function and even contribute to inflammation and disease. Because of these structural differences, cis and trans fats also affect our overall health differently. Cis fats, which are found in natural oils like olive oil or avocado oil, are considered heart-friendly. On the other hand, trans fats commonly found in processed and fried foods are harmful. They raise bad cholesterol, lower good cholesterol, and are linked to heart disease and other chronic illnesses. So, to summarize, membrane fluidity is essential for proper cell function. Cis fats support this by creating a flexible membrane environment, while trans fats do the opposite. They make membranes stiff and less functional. This shows how even small molecular differences can have a big impact on how well our cells behave. To end, let's go back to our big question. Which fat supports healthier cells? The answer? Cis fats. Their bent shape may seem like a tiny detail, but it plays a major role in keeping our cells and our bodies functioning at their best. Let's now talk about something we see every day, the fats in our food. Who here eats nuts, avocados, or uses plant-based cooking oil at home? Great! Many of those foods contain what's called cis fatty acids, which include monounsaturated and polyunsaturated fats. You'll find them in foods like almonds, peanuts, olive oil, avocados, and fatty fish like salmon. Some of these are also essential fatty acids, meaning our bodies can't make them themselves, so we need to get them from food. Examples include linoleic acid and alpha-linolenic acid, or ALA. Now here's the good news. Consuming cis fatty acids has been linked to health benefits, like lowering the risk of heart disease. So when you choose healthy oils and nuts, you're doing your heart a favor. But not all fats are good for us. Talking about trans fatty acids, of course. These are created through a process called hydrogenation, which turns oils into a more solid form, like margarine or shortening. Now, you may question, why do manufacturers do this? Well, it's because it makes oils last longer and work better for frying or baking. That's why trans fats were once common in things like fried foods, cookies, and frozen pizzas. But there's a catch. Regularly eating trans fats increases the risk of chronic diseases, especially those that affect the heart. That's why in 2015, the FDA banned artificial trans fats in the US food supply. So next time you look at the label and choose a snack, think, is this a heart-healthy cis fat or a risky trans fat? Some small choices can lead to big health outcomes. Now let's quickly summarize what we've learned today. We talked about cis and trans fatty acids, which are types of geometric isomers. They have the same elements but different arrangements. In cis isomers, the hydrogen atoms are on the same side of the double bond, creating a bent shape. These are found in healthy foods like nuts, avocados, and plant oils. In trans isomers, however, the hydrogens are on opposite ends, making the molecule straighter and more compact. These are often found in the processed foods and fried foods. So even though they look similar on paper, they are very different in terms of shapes, which can lead to very different health effects. To conclude, cis fatty acids are the good guys. They help reduce the risk of heart disease and are found in natural, healthy foods. But trans fats, on the other hand, are mostly man-made and have been linked to serious health problems, especially within the heart. The difference lies in their structure. And that small structural change creates a big impact on how these fats behave in our bodies. So always remember, understanding even small differences in molecules can help us make smart and healthy food choices every day. To end our lesson, here's a quick quiz to check what you've learned about cis and trans fatty acids. Comment your answers below. No pressure. This is just to see how well you understood today's topic.